So the mastery problem is going to be related to a classic problem in physics. It's called the ballistic pendulum. And I'll show you a short video of it in action. So this is the one that we have to work with. You can see that we have a projectile, which is that steel ball. We've got a launcher, squeeze the handle, ball flies into the little catcher, and then the catcher's at the end of the pendulum, which swings back and forth. So way back in the before times, people use things like this in order to measure the velocity of a bullet coming out of a gun, things like that you might need to know in order to do ballistics. Now we have better ways to do that, but the problem is still a handy physics thing. So we have the projectile and the launcher, which goes there, and it flies into this initially stationary catcher's mitt sort of thing that's in the end of this pendulum, and then that swings upward a certain amount. And so I'm going to look at stages of this problem and show you how they're going to work. Okay, so I'm going to insert some images here and then arrange them in time order. Okay, so here we've got the pendulum before it fires. Here we have the pendulum after, or the projectile after it's been fired, and it just has reached the catcher. And then here we have our third state, which is the pendulum has swung up to its highest point. So these are going to be our three states. I really wish that would line up better. There's not any real pages here, so I don't know why that is sticking on the line break. I'm not going to edit this one either, but you can skip ahead. Okay, so we're going to call this state A and state B and state C. And there are variables associated with these. So in state A, the ball is still on the projectile launcher here in state A. I grabbed the wrong image, but it's okay. And the spring is pulled back, and it's ready to fire. And actually, a slightly more convenient point to put it will be right after the spring has launched it. So this we're going to call mass little m, and it will have an initial speed v. The catcher by itself, here let's scribble out the ball so we know it's not there. We can use green and then it'll disappear, right? The catcher itself has mass big M, and initially doesn't have any speed, it's just hanging there. In state B, mass little m and mass big M have combined. Let's see, so this is the catcher, mass big M, and they are together now moving at a speed capital V, and the trajectory of this pair of masses in the pendulum is going to go swing up like this until it has reached its highest height. So this is still the catcher of mass m and the ball of mass little m, and together they have achieved an angle of theta, and this is going to be the highest point that they reach. So the goal overall is from this angle theta, find the initial speed v of the small mass. And we will also need a couple more things, just measurements that we can make. We need the length of the pendulum L. So this is L. It's so is this. We need the mass of the catcher, and we need the mass of the ball. And these are numbers that I have that I'm not going to tell you till tomorrow. So when we are calculating things between these states, we need to make note of what is conserved. So between state A and B, we have an inelastic collision. And you surely remember that in an inelastic collision, momentum is conserved. Between states B and C, there's no collision at all, right? They're already basically combined as one unit. And so we have a pendulum that's swinging. Well, momentum is not going to be conserved. We can see that because the direction of the velocity vectors, that direction is constantly changing. And that's because there is an external force. The external forces, at least in terms of momentum, are the weight and the tension due to this bar. But weight we can think of as gravitational potential energy. And that bar, its motion is always perpendicular to the velocity. And if you put those two notions together, we have conservation of mechanical energy. So, conservation of momentum is going to be our first equation to put together. So we have the initial momentum is equal to the final momentum. We're talking about the totals here. So the initial momentum, and I'm going to, for our convenience, call left the positive x direction, so we don't have to deal with any minus signs. So the initial momentum is just m times little v, because big M is going at velocity 0. And the final momentum is both of them together moving at speed capital V. And so far, this equation is relating a bunch of things that we don't know. We don't yet know little v, we don't know capital V. I know little m and big M, but I'm not telling you yet. So we have two equations and two unknowns in one equation at the moment. So let's go ahead and look at the next one, conservation of mechanical energy. So that means that the final and initial gravitational potential energies have to be equal to each other. That is to say that the sum of the gravitational and kinetic has to be equal in the initial and final state. Well, in the initial state, if we set up our coordinate system like we did just a moment ago, then the initial gravitational potential is 0, and our final kinetic energy is 0, because once this swings all the way to the top of its arc, it stops moving in preparation to swing back down. So we have 1/2 mass times v squared. The velocity of the combined object we called capital V, and the mass of the combined object is little m plus big M. The gravitational potential, is usually mgh. The mass of the combined object is that. And then we have our gh, and you see that the masses cancel out of this section. Now, here's the thing. We don't know h. What we know is theta. But theta is related to h. This h is the height that the arm swings up. Okay. And so we can do some geometry. So we know that this is length L right here. We know that this is length L. And so we can find this part, let's just call that D, just for something to call it. And so if we add D to the part that's left over, which is H, we should get L. So D plus H is equal to L. Well, D, this is a right triangle, so D is equal to L cosine theta. And so we put that together, we get H is equal to L 1 minus cosine theta. Okay. And we can plug that number in there. So we have 1/2 V squared equals G times L 1 minus cosine theta. And then we combine that with the equation that we have up here, which is M little v is equal to the sum M plus big M big V. So now our remaining unknowns, we'll measure theta, we'll measure L, we'll measure M and big M, and so only little v and big V are unknown. We've got two equations and two unknowns. I'm not going to finish the last step. You can look that up anywhere. Instead, what I'm going to show you is the problem I'm actually going to give you. So once I give you the numbers for L and M, and we look at the number for theta, you will have found little v, the speed at which the ball comes out of the projectile launcher. What you're going to do is look at, let me make sure I find the right picture here, this version of the problem. And if you are astute, you will note that the catcher has turned around. So it's not going to catch anything. So instead, the ball is going to fly, bounce off the back of the catcher, and the catcher is going to swing forward from that collision. What kind of collision? So instead of an inelastic collision that we had before, we're going to have an elastic, N space elastic collision. I don't think that's how you spell elastic. It might be, probably not. Okay, and that is going to be your problem. You're going to find the new theta.